As an application of all the counting problems we've been talking about so far, let's look at a standard deck of cards and poker hands. We'll do this in 2 videos. First of all, a standard deck of cards has cards with 13 different values, 1 through 13. The 1 card is usually called an ace. 11, 12, and 13 are called jack, queen, and king. And all the other cards just have regular numbers, all the cards between 2 and 10. So every card has a value and a suit. A suit is a symbol that appears on the card. This is the spade suit. This is the heart suit. This is the club suit. And this is the diamond suit. All 4 suits have exactly 1 card of each value, 1 through 13, that is ace through king. So the number of cards in a standard deck is 4 suits times 13 values, which is 52. Now, a poker hand is a collection of 5 cards. Order doesn't matter, so if you rearrange the cards in your hand, for instance, 9, 10, jack, queen, king of clubs, if I rearrange them and hold them this way, it still counts as the same hand of cards. So here order doesn't matter. So the total possible number of poker hands there are is 52, choose 5. Any 5 cards from this 52 card deck. Now that's 52 factorial over 5 factorial divided by 52 minus 5 is 47 factorial. Those are pretty big numbers. It turns out to be about 2.6 million. Right, now depending on what collection of cards you actually have in a poker hand, you might win money against somebody else who's playing poker, because some collections of cards are considered more valuable than others. Let's look at some examples of these. Now there's 4 cards of every value, because we have 4 different suits for every value. So you could have all 4 of a certain value in your hand plus 1 other card. You can't have 5 of a kind because there's only 4 of each value. So 4 of a kind is something like 4 kings and a 7. So this poker hand is 4 of a kind because of the 4 kings. So in how many different ways could we have a poker hand which is 4 of a kind? So there's 13 different values for what those 4 could be. We have to have all 4 suits, so there's nothing to choose in terms of suits. And then this last card has one of the other 12 values. and it can have one of 4 suits. So the 12 is the values for the, let's say, singleton, and the 4 is the possible suits for the singleton. So there's 13 times 12 times 4 possible poker hands that are 4 of a kind. Now we've got 2 values here, king and 7, or any other 2 values. So you might think that we should start our counting with 13 choose 2. 13 choose 2 ways of choosing those 2 values. But we don't use 13 choose 2 because the first value and the second value have 2 different jobs. One of them is going to be the 4 of a kind, and one of them is going to be the 1 of a kind. So we don't use 13 choose 2 because having 4 sevens and 1 king is not the same as having 4 kings and 1 7. 13 choose 2 would mean order doesn't matter, but here order does matter because order of the 2 values, because the first value we're saying represents the value that's the 4 of the kind, and the second value is the 1 of a kind. Alright, so this is how many. 13 times 12 times 4, 4 of a kind. Now we could possibly have 3 of a kind in a poker hand and 2 other cards. So that'd be something like king, 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 7, 8. So here's a 3 of a kind poker hand. We've got the 3 kings and then 2 other values, which are not equal to king and not equal to each other. The number of these is, so we've got 13 choices for what the value here is going to be. And then we're not going to use all 4 suits there, we only use 3 suits. There are 4 possible suits to choose from, and we want to choose 3 of them for these 3 cards. We don't need to order hearts, clubs, spades, or spades, clubs, hearts, because the order of the cards in the hand doesn't matter. These are all performing the same task. Alright, then we've got 2 cards which are different values from each other and different values from the first 3. So once we've chosen 1 value for these, then we have 12 values left to choose from for these 2. So 12 choose 2. I'm not going to say 12 times 11 because choosing a 7 and an 8 is the same as choosing an 8 and a 7. The 7 and the 8 have the same job to do here. They're going to be a single card that doesn't have the same value as anything else in the hand. And then we need to choose their suits in 4 ways times 4 ways. So I'll write times 4 squared. So these 12 choose 2 are the singleton values, and the 4 squared are the suits. So 13 times 4 choose 3 times 12 choose 2 times 4 squared. Now if those last 2 cards that aren't kings, or aren't the same as the 3 of a kind, have the same value as each other, that's a different poker hand, which is better than three of a kind, which is called a full house. So something like king, 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 7, 7. So we have three of a kind and a two of a kind in the same hand. So here's a full house. 3 kings and 2 sevens, for example. Could be any value for the 3, any value for the 2. So how many hands are there like this? The number of these is, so we have 13 choices for the 3 of a kind. And we have to choose 3 out of the 4 suits for that 3 of a kind. And then, so this other pair has to have a different value. So there's 12 values left after we've used one of the 13 for the 3 of the kind. So 12, and then we need to choose 2 of the 4 suits for the 7, or whatever the other value is. So this is for the 2 of a kind. Again, you might think that we're choosing 2 values, one for the 3 of the kind, one for the 2 of a kind. So we should say 13 choose 2. But that's not quite right, because 3 kings and 2 sevens is not the same as 3 sevens and 2 kings. They're both full houses, but they're different full houses. They're different poker hands. Alright, so that's how many full houses there are. 13 times 4 choose 3 times 12 times 4 choose 2. Alright, 4 of a kind, 3 of a kind, 3 of a kind, and a pair. Could also have 2 pairs and then 1 leftover card like this. That's not really entering into making the card the hand special. So maybe we could have 2 kings, 2 sevens, and an 8. So 2 kings, 2 sevens, and an 8. There's a poker hand which is 2 pairs. So that last card is a different value from what these pairs are. And of course, these 2 pairs have different values, because if they had the same value, it would be 4 of a kind, which is better than 2 pairs. The number of these is, alright, so now I'm not going to say 13 choices, 12 choices, because having 2 kings and 2 sevens is the same as having 2 sevens and 2 kings. So now, to choose these 2 values, we really do want 13 choose 2. So 13 choose 2 values for the pairs. And then 4 choose 2 ways to choose the 2 suits of these cards, like the kings. So 4 choose 2, and then 4 choose 2 again, ways to choose the 2 suits for these cards. "13 choose 2 the first time because the kings and the sevens, or whatever those 2 values are both completing the same task. They were different tasks, like a first pair and a second pair, then we'd say 13 times 12. But since there isn't a first pair and a second pair in a hand, you can shuffle them any way you want. It's the same. 13 choose 2 ways to choose those 2 values for the 2 pairs. All right, so finally, the last card has one of the 11 values left, because there's 13 values and we just used 2 of them for the 2 pairs. So there's 11 values and then 4 possible suits. So 13 choose 2 times 4 choose 2 squared times 11 times 4 is the number of poker hands that are 2 pairs. Another possibility for a poker hand is that it has just 1 pair in it. Something like 2 kings and a 7 and an 8 and a 6. So this poker hand is 1 pair. 2 kings are the pair. The other 3 cards have values which are different from the king and different from each other. So the number of these is 13 choices for that value. Then we need to choose 2 suits for those 2 kings, or whatever the value of the pair is. So 4 choose 2 suits. And then we have 3 individual cards that are doing the same job. They're just other values. So we've used one of the 13 values for the pair, so there's 12 values left. 12 choose 3 values for the other 3 cards. And then 4 times 4 times 4 suits. For the singletons. Alright, so I think that's all the repetition we could possibly have, except for sort of the trivial, or I should say sort of uninteresting poker hand where none of the 2 cards have the same value. If you're playing a poker, a hand like that is good only for its highest value, because you don't have anything special going on in terms of repeated values. So you could have a hand with, let's say, no repeated values. An example would be king, 6, 7, 8, 2. So king, 6, 7, 8, and a 2. So this poker hand doesn't have any values repeated, so it's not worth anything special. How many poker hands are there like that? Well, we need to choose 5 values. Choose 5 is a number of ways to do that. They're all singletons, and then each one of those cards needs a suit. So 4 times 4 times 4 times 4 times 4 is 4 to the 5th suits. Now hands with no repeated values aren't necessarily worthless. Sometimes they get counted only for the highest card there, but other interesting things can happen. We could have the values all be consecutive, we could have the suits all be the same, and those are called straights and flushes. I'll talk about straights and flushes in another video. The end.